Okay, our next speaker will be Corentin. He will be talking about the causal origin of hazy galactic angular momentum replacing galaxies in their cosmological context.
Check. Okay, yeah, I just made a tiny modification because we heard quite a lot about very high redshifts throughout the day yesterday. So let's make a small modification to my presentation. I'm going to talk about low redshift angular momentum. And the reason why I want to replace galaxies in their cosmological context is because, well, angular momentum isn't just created magically around the galaxy, but it actually traces back all the way to the cosmological environment. So, for example, if we go back to James' presentation just before, if you want to be able to build up a disk, you need to have some sort of coherent inflow of angular momentum. How do you create that from cosmological context? So I'm mostly going to talk about simulations, but before I dive into my presentation, I just wanted to give just a small overview of one of the motivations for angular momentum. So I just talked about the creation of disks, but of course there's also this pretty well established no correlation between high angular momentum contents and the presence of of disky galaxies. So disky galaxies tend to have typically 7 times, 8 times more angular momentum than elliptical galaxies of the same mass. And the other motivation is that if you look at the substructure of the galaxy, you also tend to be more bulgy if you have lower angular momentum. And the question is, what is the error of causality? Is the same parameter driving angular momentum up and down as the one that is driving the morphology, or is the change of angular momentum the cause of the change of the morphology? And also, if you trust simulations, you can also find other correlation between the angular momentum and some properties of the galaxy. So, for example, the fast rotating galaxies tend to host smaller black holes and vice versa. And so that traces back again to the question, what is causing what? And the other thing that I find interesting with angular momentum is that it's the most natural quantity you can get out of the interaction of the anisotropic cosmological environment with the galaxy. And notably, we know that at high redshift, most of the mass, most of the angular momentum is flowing along filamentary structures, which means that if we want to understand high redshift disk formation, we need to understand how angular momentum is created via torque with the cosmic web and how then it flows into the galaxy. And at lower redshifts, we mentioned earlier this morning Euclid's, if we want to understand the intrinsic alignment, so the fact that galaxies that are nearby tend to point in similar directions, and this direction happens to also be either aligned or perpendicular to the cosmic web, that tells you that there is some sort of connection between the environments and the properties of galaxies. So essentially, we can't really understand disk formation without taking a step back and try to understand the bigger context. But how do we study these effects? The difficulty is that usually we resort to large volumes in simulations where we rely on very large samples of galaxies with different stellar masses, dark matter masses, angular momentum contexts positioned in the cosmic web. And what I want to talk about today, which is the approach that I try to follow, is to instead try to focus on a small number of galaxies, but where I systematically change their angular momentum while trying to keep their stellar mass fixed, their dark matter halo mass fixed, their position in the cosmic web fixed. That allows me to create the same galaxy, but with different angular momentum, and see how it's going to later affect the properties of the galaxy. And that also allows me to understand better how angular momentum is generated, and then flows all the way to the galaxy. Okay, and so just where do we stand with angular momentum? Well, essentially, I'm going to remain quite qualitative, but essentially, we stand quite far away from the truth. The best theory we have, tidal log theory, provides us an estimate of angular momentum, which is accurate, give or take half a dex, and give or take half a dex is the difference between an elliptical and spiral galaxy. So essentially, we can't make predictions that are sufficiently accurate to make anything meaningful in terms of galactic angular momentum. But also, even if we had the halo angular momentum, there's still a huge step to be able to model what is the stellar angular momentum from that. So essentially, there are two big puzzles. First one is that the prediction for the halo angular momentum remain qualitative. And then the halo angular momentum is quite a poor predictor of the stellar angular momentum. So I want to address both of these points today, if I manage to go through all of my slides. All right, and so I want to address 3 questions today. First one is whether dark matter angular momentum is chaotic, or whether it's just that our theory is poor. And if you want to snooze your brain for a couple of minutes, the answer is our theory is poor. Then does the stellar angular momentum retain some memory of the environment? So if I change the environment, am I getting a slightly different galaxy, or is it completely chaotic? And finally, how is angular momentum transported from cosmological scales to galactic scales? Okay, and then, well, there is no spoiler here. First thing I want to address is my first point. So the way I approach this problem is to try to build numerical setups to try to understand how angular momentum is generated in the first place. So essentially, if you have cosmological initial conditions, then you run your favorite simulation with your favorite code all the way to redshift 0. You end up with a nice-looking dark matter halo. You can find its particles, trace them back to the initial conditions. And because it's a simulation, you're allowed to play God. And so you can take your initial condition and modify them slightly to add a little bit of matter in the blue regions and remove a little bit of matter in the white region. And what that achieves is that now you're creating a small net torque additionally on top of your initial conditions. And then you can run the simulation forward again, and you get a twin dark matter halo, but that has been created in an environment with slightly more or slightly less torque. And now the question, and maybe you can think about the answer to that question, if I add a small torque, am I getting a halo that is spinning slightly faster, or am I getting a halo that is spinning in a random direction? All right, so essentially the way of answering that question is to measure the specific angular momentum of the region that I just modified as a function of time. So time flows from right to left, and this is the specific angular momentum. The black curve is one original simulation, and then I perturb slightly the initial conditions of this simulation. And when I do that, I obtain these nice-looking curves. And the way you understand them is, for example, the red one. I modify the initial conditions so that there's 4 times more torquing being applied to the forming halo. And if I have a factor of 4 initially, you can convince yourself that by redshift 0, I have a factor of 4. So essentially, whether a halo is going to spin fast or spin slow is actually already written in the initial conditions. And the same holds if I decrease by a factor of 4, for example, so the dark blue line, the initial angular momentum. So what that tells us, so here, what I really did is that then I can also measure the halo mass. I get the same mass. I can look at where it is in the cosmic web. I get the same position, but the only thing that changed now is the angular momentum parameter. And so essentially, what that tells me is that the angular momentum of the dark matter, it responds linearly to changes in the initial conditions. And so if we want to improve theory, well, we need to be able to predict these curves. And also, I don't have time to go into the details, but we know you need to be able to know which particles end up in the halo or not. And that leads me to the second point. Now, if I do the same experiment, but with galaxies, am I able to spin a galaxy up? And if you imagine that here I was taking a halo and I was multiplying by a factor of almost 16 its angular momentum, can I do the same with a galaxy? And can I transform an elliptical into a spiral and vice versa? If I had time, I would take bets to know how much you trust me as an audience. So anyway, so what I did is I ran some, this time, hydrodynamical simulation with the New Horizon physics, relatively good resolution, 35 parsec, centered on halos of mass 10 to the 12 at redshift 2, high redshift or low redshift, depending on your community. And I repeated the experiment 3 times for 3 different galaxies. And for each galaxy, I modified the initial conditions for 5 different realizations, the fiducial runs, but also runs where I decreased by 30% the angular momentum, minus 20%, plus 20%, and plus 50%. And here what I'm showing is gas maps. So at the moment, it's still images at really high redshifts, but I can also, of course, animate them. And so you see that initially everything looks the same, because that's by construction, I started with almost the same initial conditions. But at lower redshift, you will see that there's going to be a merger happening here first, and then the same gamma happens here, and then it will happen here and there. And the difference is that the last major merger its timing is slightly delayed in the case where I increase angular momentum. But also if I was to plot the impact parameter, you also increase the impact parameter. So instead of shooting straight to the central galaxy, you shoot a little bit to the side and it takes a bit more time. And now what I have is like 4 realization plus the fiducial run that I'm hiding, where everything was the same, the assembly was the same except for this last major merger that's bringing a different amount of angular momentum. So what I can then do is that I know what I modified initially, and I know that everything in the simulation is going to be a consequence of that. So I have some inputs at redshift 200, it could have been 400, it doesn't matter. And then I can measure things at redshift 2, which is the end of my simulation. And notably, the left panel is only when I measure the stellar angular momentum ratio, so the ratio compared to the reference simulation. And what you can see is that if I initially decrease the amount of torque, I get a galaxy that is spinning slower. And if I initially increase the amount of torque, I get a galaxy that is spinning faster, which is kind of makes sense. But that means that the response of the galaxy is not chaotic. Whether a galaxy is going to form a fast rotating disk is already imprinted in the initial conditions. Now if I look at the baryons, so all stars plus gas, I also find that there's some correlation, except the correlation is a bit weaker. And also you have like some funny looking curve like that, where you don't really understand what's happening, and same with dark matter. And the way we understand that is that there's things floating close to the virial radius of the galaxy contributing a lot of angular momentum. And depending on which realization, this thing may be in or out, and so may contribute or may not contribute to the total angular momentum. So essentially, what is driving the apparent stochasticity of the angular momentum is just the fact that the boundary of halo is not a sharp boundary, and so sometimes you include something that you should not or should have included. But it doesn't really happen for stars because the galaxy is much better defined. All right. Oh yeah, and also it's very interesting with JWST because that means that now we have the ability of taking a galaxy, your favorite galaxy in a simulation, and spin it up or spin it down just to see what it would look like. And so if you want to test formation scenarios, then now you can do it. We have the tools to do it. The other thing that is interesting is that you can compare the stellar angular momentum to the halo angular momentum. And essentially each color here is one galaxy that I modified. And what you see is that the relation is not linear, which means that I can change the halo angular momentum without changing linearly in the same way the stellar angular momentum. So I can have a fast rotating galaxy and a low rotating halo and vice versa. But now if you take all the baryon angular momentum to the specific angular momentum of the halo, you see that they're more or less, except for this point, more or less following like linear tracks, constant retention fraction. So essentially the conclusion here is that the changes in specific angular momentum of the baryon for individual galaxies, not at the population level, but at individual galaxy level, closely tracks the one of the halo, but then the real difficulty is to know which fraction of this baryon angular momentum ends up in the disk. And that depends on your star formation, that depends on your feedback. And most likely, if I were to change my simulation, I would probably get different tracks as well. But I trust that part pretty much. All right, how am I with time? I'm going to skip that, but if you just look at the images, essentially this is the reduced angular momentum. I have something that looks like a peanut with a bit of blue things. If I increase the angular momentum, I end up with something that looks like a very nice, thick star-forming disk. So essentially, I'm able to convert something that looks like I don't really know how to classify the galaxy, but something, I can convert it into a like nice, thick star-forming galaxy by just modifying the initial conditions. All right, and the last thing I wanted to talk about is to talk about gas transfer, because so far what I've done is that I modified the initial conditions, so the cosmological large-scale environment, and then I looked at what happens to the galaxy. But of course, if I want the full story, I need to know what happens in between redshift 200 and redshift 2, apart from just dropping to zeros. Okay, so the first thing that we can do is we can follow the particles as a function of time, a bit like what James presented earlier, and then measure, for example, the evolution of the direction of the angular momentum as a function of time. Between the moments a given particle crosses 3 virial radius and 1 virial radius, that gives me these curves. So this is the angle between them as a function of the time at which it crossed 1 virial radius. Essentially, the direction remains the same. If you go from one virial radius to a third, it still remains more or less the same. But then when you go from 1/3 to 1/10 of the virial radius, all of a sudden you realign your angular momentum to a different direction. So what that means is that you generate some angular momentum at large scales, you transport it more or less keeping the direction, and then you get close to the galaxy and all of a sudden you flip in a different direction, due to torques with, for example, the disk and the inner halo. And most of the realignments happens in what I call the CGM, which is probably the inner CGM for other people, but for me that's like more or less 1/3 of the virial radius. Okay, and so what happens exactly to the gas? That's just a description of the direction of the gas. The thing that you can do is you can try to follow, and that's part of some work that has been done by the grad students, Susanna Kojan. You can track the particles and classify them as either really, really cold, so it never heats up above 310 to the 4, or really, really hot. It heats up above 510 to the 5 Kelvin at some points during accretion. And then you can try to plot the trajectories of this thing, and you see that well, cold accretion is more or less filamentary, and hot accretion is more or less isotropical. And you would expect that if you look at cold accretion, that's funneling gas efficiently to the center, and it creates star formation quite quickly. What came as a big surprise to me is that this is not what's happening. If I look at hot accretion and I plot the time it takes to go from 1/3 to forming a star, I actually find that it's typically on the order of 100 to 200 million years, all the way to redshift 2. But for cold accreted gas, it's actually much higher, which means that when you have gas that is being funneled through cold accretion, it actually takes more time than the hot mode to form stars. Note that I'm not saying that most of the gas is coming from the hot mode, it's still coming from the cold mode. It just, the gas that goes through the cold mode takes more time. There's much more, but it takes more time. And also the fun thing is that if you take more galaxies, so these are 3 different galaxies, you see that there is a drop each time you have a merger. And that looks pretty much like a sort of compaction event where you have a merger that disrupts everything, and all of a sudden you drive a huge burst of star formation. All right, and I think I'm going to stop there with some take-home messages. First, dark matter angular momentum is not chaotic, it's not stochastic, it's completely deterministic as long as you do things properly and you look at individual halos and you do a careful analysis. The stellar angular momentum retains some memory of the cosmic web. It's not chaotic either. And you can modify it in simulation if you want. And finally, there's complex things happening in the inner CGM or my CGM, where you have a sort of buffer zone from being dominated by what happened to you when you were in the cosmological environment to all of a sudden you transition to being galaxy dominated. And if we really want to make progress to understand formation of these galaxies, we need to understand how you transition from being cosmologically driven to being galaxy driven. That's it.
We can take one question, and the next speaker, please set up.
So in your last few slides, you mentioned that the hot accretion takes, cold accretion takes slower to form, and hot accretion takes longer. But the hot gas will need to cool at some point to form stars, right? So like, do you try to figure out like where that cooling happens? Like, does it happen in a CGM before you get to the galaxy, or does it cool out inside the galaxy?
So the gas that has been accreted hot and that forms stars, by the time it enters 1/3 of the virial radius, it's not hot anymore. It has already cooled a little bit from being shock heated to the time it actually reaches 1/3. But it's still a bit warmer. It's warm, it's not hot, but it's still a bit warmer than the cold gas. And what seems to be happening, and hopefully you should find it soon in a paper on the archive, is that the cold gas piles up in a sort of like extended ring around the galaxy. And just it takes time for the gas to go from the outside of the ring to the inside of the ring where you form stars. So you form stars inside out in the ring, whereas the hot gas just goes from below and above the disk and directly funnels gas to star forming region without like completely bypassing this ring. So essentially, you take a small highway if you're hot gas, except don't put a lot of gas to it.
We thank Corentin again.